Hi everyone, today I will be going over Lab 5. The first part of this is looking at the work-energy relationship. So let's go over to Pivot and look at this activity. So it does have quite a bit of information here and it's good to read it, okay? We want to understand our relationship between work and energy. Okay, so first it kind of gets you into the motions of what is going on, how to measure things in your experiment here. So I'm going to go ahead and press play, and so you can kind of see what is going on here. Okay, so we have a cart and it's pulled back and attached to a spring on the other side, pulled back by a ribbon, and then he cuts the ribbon and lets the cart move. Okay, so that's the main idea. Okay, and it tells you exactly what these different components are that you're measuring. So like the spring stretch is how far that spring stretches. Okay, and then so you practice measuring that. And we also have the velocity that it wants you to determine. So you can go ahead and follow these instructions to calculate the velocity. Okay, and then once you've done that, you can move on to the experiment portion. Okay, and so it's the same exact setup, okay, that we had before, but now we want to create a data table and take data. Okay, so we can change our mass, okay, and which spring stretch we have. So how far are we going to stretch it? And then our release video or our spring stretch video. Okay, so I'm going to show you the release video. So that's this one here. And so you can calculate his velocity as he's traveling. Then we have our spring stretch video, which is a zoomed in video or clip of the stretch of the spring. So you press play and then they move it back. So you can see that before the spring was there. So it wants you to, oops, not that one, this one, to see how far this spring was stretched. Okay, so you press play and then you measure that distance to where it was stretched. Okay, so that's that part of it. And it tells you in this data table what you need to write down. So what you need to collect, okay, for each stretch. And so you pick one of these masses. Let me see if I have that in here. We want you to pick one of the masses, okay, and anything other than the 602 grams, and then you take your data from there. Okay, so you're keeping your cart mass constant, changing that spring stretch, okay, so that distance that it stretches, or delta x. Okay, so then what you'll do is you'll make a graph of our velocity of the cart versus the spring stretch and see if there is some sort of relationship between the two. And once you find that, you'll go ahead and write that down. So in here, I say, what type of curve fit equation best fits your graph? So is it a linear equation that fits your graph the best, or is it an inverse law, or what is the best equation? Okay. Then from there, you can go ahead and linearize your data, and I have an explanation on how to do that. Okay, so for example, if my curve fit is y equals ax squared, note that is not necessarily the correct one for your curve. Okay, so don't think that because I'm using that as an example that that's necessarily the correct answer. Okay, I will then take work column in my data and square it. Okay, so then when I create a new graph, I'll have a velocity versus work squared graph. Okay, and that will make my graph linear. So my graph is now linearized. Okay, so this is what you'll do, and then from there you'll talk about the units of your slope, and then determine that relationship of work to velocity, and then there's one more portion, and that is called checking the spring constant. So now we are looking at another equation, and that equation is force equals spring constant times the elongation of the spring, or that spring stretch. Okay, so you'll do something very similar. You want to see what the force is, and then if that is related to our spring stretch, or I'm sorry, our spring constant. Okay, so what you'll do, it doesn't have any instructions. That's why I wrote them out for you. So in this video, we have one system here, okay? And if I press play, you can see what he is doing, or she. This person is putting on weights, and the mass of each of the discs is 100 grams. And you can see as they increase that mass on this side, the spring is being stretched. Okay, remember when we were looking at force diagrams or free body diagrams, okay, and we're looking at forces and so forth, this would be one continuous system, right? So we've got force of gravity pulling this guy down and therefore stretching this out. Okay, so we will have some force, which is due to the gravitational force, and we'll have our spring force, okay, or K times X. So what you'll do is you will calculate that force of each mass as each mass is placed on the system. So as the mass increases, you'll take that force calculation and the elongation of the spring each time, and then from that you can calculate your K. Okay, and so you'll do that, create a data table, create a graph, what's the equation of your graph, and what is your spring constant from that equation. Okay, so that is all for the first part of the lab. So we are looking at a lot of spring constants. Okay, so the next part, part 2, is looking at power. So power, while this person runs uphill. So let me go ahead and show you what this video looks like. So there's this woman running uphill. She's an Olympian. And so you're going to determine how much power she's exerting. Okay. So, it tells you what to do. It tells you that the power is work done divided by time. Okay, so you want to, let's see, select one of the trials without the backpack, make measurements, and calculate to determine the power her legs produce to offset the work done by the force of gravity. Okay, and then says, assuming she did produce the same effort, what is the mass of the backpack? So you're trying to then determine the mass of this backpack given what you had just solved for, and then kind of checking your answer and so forth. And it has one more question. Okay, so this one's not as in-depth as the last one, but hopefully this helps you out. And so we'll see you in the next video. This was Lab 5.